Hello everybody and welcome back. In this module we are going to be further exploring the Pythagorean Theorem, how we can apply it to a variety of real-world situations, and also how we can apply the Pythagorean Theorem to help us find distances on a coordinate plane, which will lead us to use something called the distance formula. Let's get started. The first thing we'll review is just what the Pythagorean Theorem looks like. And we all recognize it as a squared plus b squared equals c squared, where a and b are the legs of a right triangle, or the shorter sides, and c is known as the hypotenuse, which is always the longest side and opposite of the right angle. And we know that we can apply this situation to solve for any of the three sides of a right triangle. When we apply the theorem to real-world situations, sometimes it can be a little bit more challenging to identify where that right triangle actually exists. For example, we have this three-dimensional rectangular prism here on the right. In one situation, we could consider just one of the surfaces of this prism, like this front face here, and in this situation it can be a little bit more obvious where we could find right triangles. For example, we could consider the height of the prism here and the length at the bottom, and then connecting those opposite corners we create a right triangle with the right angle in the bottom right hand corner. That one is one that many people would be able to identify pretty clearly. However, we could also work across this prism and find a right triangle, something like this. We could potentially consider this height in the back left corner and connect that then with the vertice or the corner down here along the bottom face of this prism. I'm trying to make it a little extra bold here. And then connect those opposite corners. And what we actually end up with is a right triangle that spans across the entire prism, with that right angle being back here, as the corners of any point in this prism are at a 90-degree with their connecting faces of the prism itself. And it's sometimes the ability to see these right triangles across three dimensions that can be a little bit challenging. So we wanted to make sure that we gave an example of what that might look like here. Now, there are many other locations in which we could identify right triangles on a prism such as this, but we'll use this one just as a quick example to look at first. For example, if we knew that the bottom side of this right triangle was, say, 15 feet long, and then the side running from corner to corner was actually 20 feet long, we might be asked then to find the height of this prism in this situation. So of course step one is to figure out which sides are our legs and which side is the hypotenuse of the triangle. Keep in mind that the hypotenuse is always opposite of the right angle, so with the right angle being in the lower left, we can see that it clearly points towards the 20-foot side. So we do know that that 20-foot side, that is going to be C, which means the other two sides, of course, are our legs. Remember that the legs, A and B, are interchangeable, meaning either one can be the 15-foot side and either one can be the missing side. So it's really just up to you to choose which one you want it to be. And then we'll just substitute in our values where they go into the Pythagorean theorem. I'm going to go ahead and call my 15-foot side A, just for this situation, which means that I can substitute it in as 15 squared plus side B squared, which we don't know, which should equal side C, which is 20 feet long, squared. And then we'll go ahead and find our squares. 15 squared is 225 plus B squared equals 20 squared, which is equal to 400. After that, we'll go ahead and solve by isolating the variable. So we'll subtract 225 from both sides and simplify. And I wrote that incorrectly, got really excited there. Try 225 this time. And 225 minus itself is 0, so that constant is gone, leaves us with just b squared. And 400 minus 225 is 175. And the last step to isolating that variable would be to do the inverse of squaring b, which is to do the square root. and we'll perform that to both sides. Of course, the square root of b squared is just b, and then we'll do the square root of 175. Now, 175 is not a perfect square, so this would be a time to make use of a calculator unless asked to estimate by hand. The square root of 175 comes out to be at least rounded to the nearest hundredths place. I think is going to be plenty. I'm going to say is approximately 13.23, and I did call these feet, so feet. So that would just be one example of how we could use this. In this case, I did find a missing leg of the right triangle, which happened to be the height of our prism. So that's just one way that you guys are going to apply that this week. Next, though, we're going to focus on using the Pythagorean theorem on a coordinate plane. So here on a coordinate plane, finding the distance between certain locations can be relatively straightforward. For example, if we had a point at 1, 4, like this, and a point at 4, 4, like this, finding the distance between these two points on a coordinate plane actually doesn't require much effort because these points are directly either left or right or above or below each other, meaning they follow the grid lines. I could simply count the spaces between them, 1, 2, 3, and realize that the distance between them is 3 units in this case. So that one again is pretty straightforward, again because you can see it, but we could also look at the ordered pairs, 1, 4, and of course 4, 4, and realize by looking at those that finding the distance between them would be straightforward. Reasoning being that if you see ordered pairs where one of the values is identical, being either the y values, like they are here, or the x values in another situation, if one of the values is identical, we can simply find the difference between the other 2 points. We would ask ourselves simply what is the difference between 4 and 1, so 4 minus 1, and that would give us our same distance of 3 that we started with earlier. Of course, again, like I mentioned, that's the basic version of finding distance, but what if we changed this slightly? What if instead of having our initial point, which was at 1, 4, what if we switched it to 1, 3? Now, while the distance between now our new point and 4, 4 isn't much different, we can clearly see that the line between these 2 points, or the line segment between these 2 points, is a little bit different, and it doesn't follow those grid lines anymore. And this is where we can start to apply the Pythagorean theorem to help us find out how far apart are these new points. Again, going back to something I said earlier as well, though, we can't simply count a gap between them, because notice that the x values are now not identical, 1 and 4, and the y values certainly aren't the same anymore, now being 3 and 4, so that's why we need a new process to find out what's going on. So what we're going to do is we're going to have to imagine that we have a right triangle somewhere here that uses this blue side as one side of the triangle. Specifically, it's usually going to be the hypotenuse of that triangle. So what we can imagine here is that we're actually going to create these extra sides of our right triangle right here, and now all of a sudden we have a right triangle where we can count the sides of the legs and then solve for the hypotenuse, our blue side here, which would help us find that exact distance. There's typically going to be at least 2 ways that you could imagine this right triangle to exist. I'll show you another one here. Instead of drawing the right triangle below the blue side, we could have also drawn it above, and you're still going to find the exact same information, so just be ready to be a little bit flexible with your thinking in these cases. I think I'm going to leave it like this for this situation and go ahead and use the Pythagorean theorem to help us find that missing side, which again is our hypotenuse. It is opposite of our right angle here. All right, that means the legs are going to be, of course, now 3 units, which we knew from our earlier work, and the left side here, which is 1 unit. And again, you can call either side A and the other side B. I'll call A the 1 unit side, so we have 1 squared plus B, which is 3, and then squared, which should equal the hypotenuse, our missing side C. and solve from there. 1 squared is 1. 3 squared is actually 9. And we're going to solve for c squared. 1 plus 9 is, of course, 10, which is equal to c squared, but we need to find the value of c, so we'll have to use an inverse operation, which is to take a square root, and the square root of c squared is finally just c, and then we'll need to find the square root of 10 itself. Of course, 10 is not a perfect square, so we would either need to estimate by hand or more likely use a piece of technology like a calculator. And we'll usually estimate square roots out to either the tenths or the hundredths place. I'm going to do the hundredths place for precision's sake right now. And the square root of 10 comes out to be approximately 3.16, which means that that side C, that blue line, was actually about 3.16 units. Now that doesn't seem like a big change in such a small example like this. Remember, originally our red side was just 3 units long, and then when we moved that first point just slightly, we actually discovered that now that line segment becomes 3.16 units, so it got a little bit longer because it's now that diagonal line. So you're going to be using that idea a lot. You're going to see 2 points on a coordinate plane, and you're going to find the distance between them using this Pythagorean theorem to help you. Let's take a look at another. Now this example you're going to get to try by yourself as well, so you'll get an opportunity to pause the video. And this time we're going to have 1 point at -3, 1, and the other point is going to be at 3, 4, right here. So your job would be to find the distance between these 2 points using the ideas from just a little bit ago. So I'd like for you guys to go ahead and take a moment, pause the video, do the work on your own, and see if you can't discover the length of the side by either drawing in or imagining where an imaginary, right triangle would be. At this point, you should either be preparing to quickly pause the video, or you should already be done with your attempt at this problem, because we're going to take a look at the solution now. So I'm going to imagine that the other sides of the right triangle fit right here, the right angle being in this lower right corner. Of course, this time meaning that since I wanted to find the length of the red side, which is the hypotenuse, it is C, the other 2 sides would be my legs, being A or B. I would want to go ahead and find the length of each of those sides. And after counting, I would discover that A equals 6 units and B equals 3 units. And with all that information, it would be time to go ahead and use the Pythagorean theorem to see what we could figure out. So if you identified the correct side lengths, you were off to a really good start already. Even if you drew your imaginary right triangle above the red line instead of below it, this would still work out if you were careful. And of course, your A and B could be reversed, and that's not going to have any bearing on your solution either. Alright, if A is 6, we're going to do 6 squared plus B, which is 3, so 3 squared equals C squared. 6 squared is 36, and 3 squared is 9. And our last step here, or steps I should say, we'll do 36 plus 9, which is 45. And then take the square root of everything. And since 45 is not a perfect square, again, you're going to want a piece of technology here to figure out that the square root of 45 is approximately 6.71 units. And there you go. So if you got around 6.71, you did a great job, and congratulations on that. Now as we go to our very last step for today, what I'm going to ask for you guys to pause and take a look at are the actual ordered pairs that define our starting points. Of course, our first one over here, that was at -3, +1. And our second one was at +3 and +4. Because at the beginning of the video we did say we were going to talk about something called the distance formula. And in essence that's what we have been using in the following ways. We're going to pay attention to these ordered pairs because it's actually something about these numbers excuse me, that helped us find some of the values you see here. Notice that in the example a few minutes ago and then this one here, the process looked exactly the same. We drew an imaginary right triangle. We then counted the side lengths of the legs of the triangle in both situations. And then we squared those values, added them up, and then took the square root of that sum. That happened every single time, which really means that we could shorten this whole process, since the process is very repetitive, by solving basically for C in the whole situation that happens. But there's a couple things we need to clarify. It's where would we get A in that situation, and where would we get B in this situation, if we're going to kind of accelerate the process closer to the final step. Well, let's look a little bit more closely at that. When we talk about finding A, of course we could just simply count the side length, 1, 2, 3, 4, 5, 6 units long. That's where we got our 6, that makes sense. But we could also use the ordered pairs as well, because when we count from left to right, we are exploring the difference in the x values. Well, the difference in the x values comes from these ordered pairs right here. Now, when we find that difference, we are going to find the difference in the x values, but we can't simply say we're going to subtract x from x, because, well, they're both x values and that doesn't make sense. So we're going to have to identify some kind of difference between them. So I'm going to call positive 3 here x sub 2. We'll call x2. And the negative 3 we're going to call x sub 1, or x1. Now, you're going to want to know, well, how do I know which one to call which? Generally speaking, the point that is further to the right, which of course would be from this ordered pair here, that's our x2, or our second values. The ones on the left are our first ones. And that'll be a process we use quite a bit. So we're going to take x2 minus x1. And again, we do that because here, if we had done that, that would be 3 minus negative 3. And 3 minus negative 3 is actually positive 6. And that's where we got this side length of 6 here. So that would be how we got, or how we find the value of A. So in our formula, what we normally do for the Pythagorean theorem is we take A, which is what we're calling x2 minus x1, and we square it. Of course, what do we do to that? We add b squared. How do we find b squared? In this case, notice that the side b was our vertical side. And when we explore the difference of a vertical change on a coordinate plane, that affects our y values. So similar to what we did with the x's, we're going to take y2, and we're going to subtract or find the difference from y1. In this case, that would have been 4 minus 1, which really gives us 3, just like we saw to start. So we know that works. So in our new formula, we're going to do y2 minus y1. And just like in the Pythagorean theorem, we had a squared plus b squared. So we are going to square this second value as well. So that's what we've done so far. All of this kind of looks fancy, but it's just asking us to find the difference between the x values and the difference in the y values, because those give us the legs of our right triangle, A and B. So we're just creating or recreating this part of the Pythagorean theorem. Now, of course, after that, after finding their squares, we would add them together, just like we do here. And then that final step would be to do the inverse of squaring C, which is right here, we take the square root of both sides. So right out of the gate, what we're going to do is we're going to imagine that we've found the difference of our x's and squared it. We found the difference of our y values and squared it. Then we've added those two values together, and after that, we're going to go ahead and square root the entire end product of that whole process. And once we've done that, then we would be at our final step, at least an estimated version or approximate version here, which will be what we're now going to call D, or the distance, go ahead and write that out, between any 2 points. So if we follow what looks like somewhat of a messy process, but realizing that it all just comes from the Pythagorean theorem, we can find D, or the distance between any 2 points on a coordinate plane, by applying this formula. So I'm going to give you guys one example that you can try on your own of applying this distance formula, and then of course you'll get to use some of it as well in your practice during your lessons for this week. Let's go ahead and take a look at an example of how you can use the distance formula. Okay, so here's the distance formula one more time. D, or distance, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And your job is to find the distance between the following 2 points. I'm going to look at -1, and +2, +5. So this is your time to go ahead and pause the video, take a few minutes to think and try to work through the problem. Just as a little hint or a side note at least, of course, we have to figure out which one are our second points, our x2, y2s versus x1, y1s. And keep in mind that the tip was that the point that is found further to the right on a graph, those are our x2 and y2 values. So you have two options here. You can actually find a coordinate plane and envision where these go, or you can use the x values to help you. The larger the x value is, the further the right it is on a coordinate plane, and you can use that to explore that here. So again, go ahead and pause the video, take a few moments, and then we'll take a look at your solution here. Okay, let's go ahead and take a look at your solutions and see how you did. So first things first, which are our first values and which ones are our second values? +2 is greater than -1. That means 2, 5 was our second values, meaning x2 and y2. -1 was x1 and y1 then, which means I know where they go in the formula, and I can go ahead and get ready to use my distance formula. I can find out exactly how far apart these are. All right, x2 is 2 minus x1 is -1 squared, plus y2 is 5 minus y1 is also -1, and we're going to square that. All right, do the square root. All right, so first thing is 2 minus -1, which is actually 3. So we're going to do 3 squared plus 5 minus -1, which is 6. So we're going to be doing 6 squared. I'm going to go ahead and move up a little bit here. All right, take the square root of that. 3 squared is 9. 6 squared is 36. And add that up. 9 plus 36 is 45. And this is familiar from our work a little bit ago. And we know then that the square root of 45, which is not a perfect square, would be approximately 6.71 units. Since we didn't give any specific units, we just call it units. Well, how'd you do? Hopefully, you found some success, or if nothing else, were able to identify any places where you felt a little bit stuck earlier. But again, the distance formula is simply a very specific application of the Pythagorean Theorem, and will help you guys apply that idea to work with a coordinate plane. But those are the big things from this week. Please take your time to re-watch this video as much as is necessary, and good luck. I'll see you in class.